Hey everyone, how are we doing? It is the start of Wednesday's office hours. Oh my gosh, it's Wednesday. Hey, what's up, Marcus? I'm doing well. You doing well? Awesome. Ubot's in the chat right there. Ryan, let's throw 100 points. So what are we going to do today? What material? What are we going to learn? What are we going to practice? It's your call. It's your office hours. It's time to learn together. That's what we do. We practice and learn how to do work and assignments here. Awake Chocolate is sending me win free Awake Chocolate. Ooh, Awake Chocolate's some good stuff. Pulling up the assignments right here as we talk about it. Let's see what people want. Chapter 14, using the T-tables in the housing market. Oh, cool. So, well, with T-tables are interesting stuff. So we won't use T-tables. What we'll use, where will we go, Caitlin? Not use T-tables, though. A lot of older type things say to use T-tables. So we won't use T-tables. Does anyone know for 100 points where we will go? Where will we go? Where will we go? Does anyone know for 100 points? Where we always go when we have to do normal curve or T-curve. So where will we go? Let's go here. Yep. Drop it in the chat for 100 points. So here we go. This is what we'll start class with today. So where do we go? Let's put the notes in here. Using the T-table. Oh, just apps right there. Killing it. 100 points anyways. Oh, I hit 150 by accident right there. It's just APPS. I didn't put I should put an exclamation mark on that one too. That way if people do either one, it'll go to it. So stat 201, chapter 14. Using the T-tables. Okay, let's go check it out right here. Here we go. Oh, it's just right here. I'll drop it in for you. There it is right there. No exclamation. You know what I'm going to do? Since people do that one right there, I got to bring up Mubot. Let me go to commands, just kind of making this so here. Let me go to, a lot of people do it with the, right there with the extra. So let me go here and let me edit. Let me take this right here, submit. Let me go to plus new command, exclamation mark apps. And there we go right there. And then let's make another command and say applet, because a lot of people say applet too. And then let's put it in there. And there we go. So now if you do that right there, it should do it. So that I just updated the commands. So now there's multiple commands. Woohoo! Okay. How in the world are we going to solve this problem? So we talked about this a bit yesterday, and we'll kind of do a little bit of review right here. And these are the things to know. T-scores are basically what scores? T-scores are basically what scores? So don't think of this as just solving the problem. Think about this as understanding what a T-score is. For all intensive purposes, and think 95%, when have we heard this before? T-scores are basically what scores? T-scores are basically, and I said it a moment ago if you listened in closely, T-scores are basically this. And I'll differentiate between them here in a moment. But T-scores are basically this. Like when you hear a T-score, you'd be like, oh, it's a standardized metric, kind of like a Z-score. Great job, Kaylin, right there. So here's the thing. When you think 95% confidence, what number do you think about? When you hear 95% confidence, what number do you think about? What number do you think about? When you hear 95% confidence, what number do you think about? Well, 0.95, but think about standard deviations. When you think about 95, you think of how many standard deviations? 2, right? So we could try 2, and I don't think we'll get it right. We're going to be close. It says we're not right. Now, people might say, well, I've been doing Z-tables, and I know it's 1.96, which is the Z-score, the exact Z-score for a 95% confidence interval. We'll show this here in a second. And then you do it again, you get it wrong. But here's the thing. We'll see the difference between T's and Z's. The answer is probably going to be closer to about 2.11. And let's show it. That might be the answer. I'm not going to put it in because I only get 3 tries at this. We'll double check. That sounds way too big, Ryan. Good, Ryan. Good guess right there. I think, and I'll show where you're currently at. So let's show this right here. So, oh, there it is. Marcus has it. And Marcus, we might be within the margin of error. So Marcus 2.09 is going to be to 2 decimals. So Marcus has it right there. And let's show how Marcus found that answer. So we have to go over here and click the student T distribution. Does everyone see this? Student T. This is currently the normal curve. This is the student t. Now, here's what the t looks like. Does this look exactly like your normal curve? Like exactly like the normal curve? Yes or no? There's the normal curve. Here's the student t. Does it look exactly like the normal curve? So it's called the t distribution a lot of times. In longer terms, Gossett student t. He made up a pseudonym. Student was the person who submitted it to the journals. Does that look just like the normal curve? Like perfectly like it. Here's the normal curve again. Here's the t. Do they look identical? I mean, do you see the image change? Like here's the normal. Here's the t. Yes or no? What do you think? Does it look identical to the normal? What would we say about the t? Is it identical? Thoughts on this? Here's the normal. Here's the t. I would say it's not identical, right? But we get an additional thing to enter in here called what? And I need you to recognize this. This is huge to the t curve. Every t curve will always have with it a what? So you have to type this in the chat, or you have to see this because you have to know every time we do the t, we have to know its what's. Every time we do the t, we have to know its what's. Degrees of freedom. Great job, Marcus, right there. Degrees of freedom. Now, for the one sample t, the formula is n minus 1 for degrees of freedom, which is sample size minus 1. If we think about our problem over here, what was the sample size used to create this problem? So remember, for the one sample t, and just remember one sample t, n minus 1, what was the sample size? It was 20. So 20 minus 1 would be 19 degrees of freedom. I could go into more what degrees of freedom mean and what they are and how they're calculated. But just remember right now, for the one sample t, that's a good way to memorize it, the one sample t, when we're testing one mean, has n minus 1 degrees of freedom. So there was a 20 sample size, which led to 19 degrees of freedom. So why are degrees of freedom so important? Well, degrees of freedom show you the shape of the t. And as degrees of freedom increase, the t starts to look what? Say it with me. As the degrees of freedom increase, the t starts to look a lot more what? As the degrees of freedom increase, the t starts to look a lot more normal. Now, and great job, Marcus. Excellent work in reviewing this right here. So you notice that you have to know the degrees of freedom, which makes the t a family of distributions. We call it like a different, there's the t with 1 degree of freedom. 2 degrees of freedom show you the shape of the t. And when there's low degrees of freedom, it's the least normal and it has thicker tails and is more narrow at the center. There's a question on that on the homework and the quiz also. So you can see here it's more narrow at the center. You can see right here on the center, it's more narrow and has thicker tails with more area. And it even goes out further. And as degrees of freedom increase, it approaches the normal. So if we had a lot of degrees of freedom, I could tell you that the 95% confidence interval is going to be about 1.96. And you see it's closer, but it'll approach 1.96 as degrees of freedom increase. And we could just start typing 9 and show that it approaches 1.96. It never technically reaches it. If we carry enough decimals, you can see here that it's just going to get closer and closer and closer to 1.96. And even 1.96 is not exact. It's 1.95996 or something if you go to more decimals on it. So it approaches the z-score. So here's the thing. All we have to do is type in the 19 degrees of freedom, and there's the answer. And better yet, we round it to 2 decimals with the applet, and it's 2.09. There's a little give on this question. I might have got it right with this. We did get it right with our third guess right there, so we got it within the boundary. Now here's the thing. Remember, t's are like z's. So I've memorized all the z-scores, and I know this is 3.3263, so I'm just going to say 2.35 and get the answer correct. Because Brian saw that here on this question there was what? I saw that there was a very high, and usually after about 50 is pretty high. After 100 is very high degrees of freedom. Once again, this is not how you'll do it on the test, but how am I understanding and answering these questions without the applet? Which is kind of a cool thing to know, that we don't always need the applet, but the applet's going to get us the exact answer. When the degrees of freedom are high, the t-score is very close to the what? When the degrees of freedom are high, these are good notes to have, when degrees of freedom are very high, the t-score is very close to the what? When the degrees of freedom are very high, the t-scores will be very close to the what's? The z-score, exactly. So I knew the z-score, so I basically went a little more extreme than the z-score. because the t will always be for intervals further out because the tails get pushed out. So if you want to solve this one, which I would suggest solving right there, let's go over here and we go here to 98 and then we put in, it was 89 degrees of freedom, and there's the exact answer. I think it was right there. So let's go grab that. It is 89 degrees of freedom with 98% confidence. So that is what we have right there. Really good stuff and good work on it right there. Close down all these. Don't dive. There we go. But does that make more sense, Caitlin, right there? How are you doing on these problems? It's really fun to do like different versions of these. Let me pull up another version because I like practicing these and making sure you can get them. Like when you realize what's going on right here. Good, yay! 99% confidence. This is a tough one to guess. The z-score for 99% confidence is 2.5758 because we're close to like 3 standard deviations at that point. So this is going to be like 2.73. Yeah, this one's a very hard one to guess. Oh. We got it. And so all we have to do is 99 with 26 degrees of freedom. You go over here and you put in 99 or 26 degrees of freedom and 99% confidence, 2.78. And then I like that they give you more degrees of freedom on this one. So the z-score for 90% confidence is 1.645. So we need to go a little bit further out than that. So 1.70. And we got it right. So once again, you're not meant to guess these. You're meant to understand how T's and Z's work. And you can just enter in the values over here, 90% confidence, and it was like 52 degrees of freedom. And then, but if you understand how the Z's work, then you've been doing normal curve stuff over here where you enter in like 90% confidence in between. So I know the Z scores a lot of times from doing them so many times. And then I know the T is always a little further out. And for higher degrees of freedom, the T and the Z are very close. For lower degrees of freedom, like if you said with 3 degrees of freedom, here, try this one in the chat real quick. What is 90% confidence with 3 degrees of freedom? So my guess for that, so see if you can solve that. 90% confidence when there's 3 degrees of freedom, which would come from a sample size of 4. So my guess is like 3.8. 3.80. That's a very hard one to know because there's so little degrees of freedom that the T and the Z are going to be massively different. So I really can't take a good guess at that one. Like I'm like, we got to go look that number up. Like if they asked me that on Pearson, I'd be like, yeah, that's the T and the Z are very different at that point. Like conceptually speaking, once again, for low degrees of freedom, the T is most divergent. For anyone wondering, I do like the extra bit of info. William Gossett, who worked at Guinness Beer, realized for small sample sizes, we underestimate the standard deviation because we don't get outliers. So he added in extra variation due to small sample sizes. So the degrees of freedom are related oftentimes to sample sizes. And so when you have a small sample size, you're going to increase the amount of variation in the distribution, which puts more area in the tails. So really great work he did right there, showing that he actually creates 95% confidence intervals. No one took a guess, or no one looked it up. Here we go to T. We go to the applets. Remember, once again, go to the apps right here. Degrees of... Hey! Oh, it's really that close? Great job, Marcus, right there. Wow, I'm shocked it's actually that close. Thank you, Marcus. Good practice. There it is. Yeah, we got one more from Caitlin right here. And then we'll do the Canvas content. So once you get these down, you know how to do them. But also, once again, it's not just about looking up these numbers. It's understanding what these numbers are. Like, you can see it's a confidence interval because it's the between values, which is how we make confidence intervals. You understand that T's are always going to be a little bit bigger than Z's, and they approach the normal curve, the Z scores, as we get more degrees of freedom. It's not about just punching numbers in. It's about understanding what you're doing right here. And that's where, if you understand what you're doing, you could go here and say something like 2.04. Check your answer. You're good. And then you see that, and you say 2.36, and you're good. And you solve the question without the applet. So, of course, you have to memorize the Z scores, which don't do that. Anyways, the next question right here, Caitlin had one more, and then we're going to go do the Canvas content, it sounds like. The housing market. The housing market right here. Cool. Okay, so let's see what they want. It looks like they're giving us summary statistics. I'm going to mark this question. But while I mark this question, what do we do for any sort of question we have? Any question we have, we start by doing what with it? What do we do? Any question we have, we're always going to do what? You know it, you love it. It's time to do it for every question. Before we even read what they tell us, what do? We're not even going to read what they tell us. Don't read their question. Don't look at what they're asking you. Think about what you have.
Notation, brother.
All that notation. So what is any of the notation right here? And I need help with the notation right here. I think we have 3 things of notation. So what do we got? What do we have in this question? Any of the notation to start out? I know the equation we're solving, so that's a big hint. But you probably wouldn't know the equation we're solving yet without marking the notation. Any of the notation. And once again, if you're watching this video in the future, this is the practice for the test. Don't even read the questions. Don't look at what my person's asking you yet. Think about what you're doing and why. You're given information here about the market and losses. People had an average loss of $9,329 with a standard deviation of 1,289. This came from a sample of 32. That's the information we need. Sample of 32, average loss of 9,329, standard deviation of 1,289. So what is the notation? Good job. N equals this. And then what else do we have? What else do we have? Now we get to the tougher ones. Don't worry about getting it wrong. 100 points for each one, right or wrong guess. Great job, Caitlin. Yep. Oop, I can't even write S these days. Yep. Lowercase s, which you did put. And then 1 away. You're 1 away. 1 away. Y bar. Caitlin, great work right there. Yep, and I think you're putting your numbers in the chat. Yep. So Y bar. Yep, and so that's the sample mean. Oops, I wrote your number. See, I'm gonna get it wrong now because I'm gonna do that. That's how I get it wrong. So we have the sample size, the sample standard deviation, the sample mean. Know your notation. The more I say this, make sure write these down in your notebook right now. Once again, it's not about solving one problem. It's knowing that Y bar is the sample mean, S is the sample standard deviation, and N is the sample size. A Y bar will always come from a sample size, so you have to know the sample size for the amount your sample mean came from, such as with sample standard deviation. So with this right here, we're probably going to be solving the formula Y bar plus or minus T star, N minus 1 degrees of freedom on this. Check out the previous section. We just talked about that. Why are we currently stuck, which we really can't solve this yet? I guess I'll give this one away. Thank you, Kellen, for all those great answers. We don't know what % confidence they want for this. We can know the degrees of freedom. Degrees of freedom, that's DF right there, is N minus 1 for a 1 sample T, which is 32 minus 1, which is 31 degrees of freedom. Degrees of freedom equals 31. And degrees of freedom is this quantity right here. Hence, it is N minus 1. So there are 31 degrees of freedom. So marking your notation before doing all this is going to set your mind in place, and the degrees of freedom tell us which T we are using. So very important right here that we know all of this before we start working on the question. Okay, what assumptions do we make? Oof. So the assumptions we have are random, 10%, and then we pause, and then we remember we are doing quantitative data. So actually, which of these can we eliminate? A, B, C, or D? Which of these can we eliminate? Because remember, we're doing quantitative data. So which of these answers can we eliminate because we're doing quantitative data? Since we're doing quantitative data, we can eliminate D because D has success failure right there. And we can eliminate this one because it has success failure. So we're just down to A and B now. So we've got a 50-50 shot of getting it correct, but we're going to make sure we get it correct. Great job, Marcus, right there. Once again, with quantitative data, we are going to be doing the nearly normal condition. So let's take a look. The data are assumed to be independent and from a normal. Check the independence. Check the independence assumption with the nearly normal. No. Check the independence with the randomization. So sometimes my Pearson puts randomness checked with independence. We just call it randomness. So if it is random or independent, we're basically good, i.e. things that are independent are going to be random. And so that narrows it down to this right here. Just a quick note that sometimes they break it apart into an independence and a randomization condition. But really, I like to say they're random because if they're random, they would have to be independent. But usually we just say a random sample was taken. And yeah, it's like what assumptions would have to be checked. So they're not even telling you that they're checked. And now look what we get. We get the percent confidence. So now, once again, drop it in the chat. I want everyone to know where to go. Where do we need to go for 100 points to solve this out? So we almost have the answer. We were just told 90% confidence, which is why that star exists. That star is relative to the confidence. So where do we need to go? Boom. Oh, wait, with the S on the end, with the S on the end. So, yay, Caitlin, another 100 points. Yep. I also made so the exclamation mark works too. Okay, it's a series of apps right here. So when you go to the apps page, you need to make sure you are clicked in on the student T. You'll probably go to the normal to start, but you need to go to the student T. With the student T right here, you'll notice that you start with 1 degree of freedom. Good to see you here, Meredith. So we need to enter in our degrees of freedom, which change the shape of the T for a T with 31 degrees of freedom. You can just click 31. So you can just type it in, but you do get to see the animation of the T going to be more normal as you increase this right here. Now for confidence intervals, which one of these should we click? This is the greater than test. This is the less than test. This is a two-tailed does not equals test. When you do a confidence interval, make sure you've clicked what? For a confidence interval, like a usual confidence interval, there are other confidence intervals that we don't really talk about much, but for your usual confidence interval, we should click the what button? Should we click the greater than test, or that's the less than test? The greater than test, the does not equals test. We want to click between. Great job following along. So this is going to give us the T-score we need. I would probably carry it to 3 decimals. You can always carry to 4 if you want, but 3 is probably going to be good. Do realize you do get to round right here, so any question that wants you to round values, you can use the rounding in the app to do it yourself. So now that we have all this right here, and thank you, Adam Spanbauer, once again, 1.696. So let's go bring that over here. And all we have to do is what now? So the T-score relative to 90% confidence is 1.696. All we have to do is what now? Just plug in the values, right? So we've marked everything 1.696, and then standard deviation is 1289 over square root of 32 plus or minus 9329. 93629. Oh my God. 9329. Can't talk today. There's the 6 is confusing me. Okay. So let's take a look. Let's do square root 32, divide 1289 by square root 32, times that by 1696. And we have just computed the what? Very importantly, I always compute this first. We have just computed the what? Mathematically, that is the what there. 2 letters will let me know what you know what we're talking about. Consists of your level of confidence and the standard error. So these 2 values are your confidence level and your standard error, and together they make the margin of error. Great job, Caitlin. So understanding that this whole thing is the margin of error, and it consists of your confidence level dictated by the T relative to the percent confidence, or a Z if it's a Z interval, and the standard error is the standard error of the mean right here in this instance. So the value we have for the margin of error is 386.46. And then we just have 9329. And then we just have to find the lower and the what of the interval. The lower bound and the what bound. So the lower bound is going to be subtracting this. There's the lower bound, 8942. The upper bound, yep. And then we just add it. Now, what I usually do is, since I've already copy-pasted the margin of error, I just add it twice to get back to the center of the interval. The center is the estimate, and then the top of the interval is 9715. There we go. And that's got it. So once again, now what we want to do, this is the average loss people had. So I'm going to pause right here because interpretations are on the final. For 500 points, this is the average loss people had. Please interpret this interval. So take a moment right here. Remember, average loss people had. I'm going to write it down below right here. I'm not going to write the full thing, but I want you to interpret this interval. This is very important to the test. So if you're watching these videos and you want to get good for the test, they might not have us interpret this, but we need to interpret the interval every time and know how to do it and just be like, easy. It's the average loss people had. I can do this. So we say I am blank percent confident that the true blank is contained in the interval blank to blank. So what in the world are we going to say right here? Is the average loss people had. Remember, once again, it's not about solving this problem. It's about knowing how to do the work on the test. So don't think about it as just getting this right, because I don't think my Pearson even asked it for this one. So if you're watching this, you should be able to write this out as a sentence. We're throwing 500 points in the chat. If anyone can write this as a sentence. Full sentence right here. Full sentence interpreting the confidence roll. What did we just do right here? What is the full interpretation? Remember, you will be typing this on the test, something like this. So doing this now and practicing this now is a huge help to remember. So even if you're watching this in the future, just try typing it out, try saying it out loud. You won't be typing on the test, I am blank percent confident that the true blank is contained in the interval blank to blank. You'll have to input the blanks right here and understand what is said and what is meant. So what is it? Remember, this is gonna be on the test. The test is worth a lot more. It's the final. Well, I might get the 500 points for myself. We'll give it 5 more seconds right here. 5, 4, 3, 2, 1. So we would say, I am 90% confident that the true average loss people had, because we're estimating the true, here's the context right here, the average loss in home value, the true average loss in home value. So I am 90% confident that the true average loss in home value is contained in, so that's the context you need right there. I am 90% confident that the true average loss in home value is contained in the interval here to here. And we'll just put those numbers. So once again, this is the first, the second, the third, and the fourth thing. So there's the third and the fourth. There's the first thing, and there's the second. Meredith might have it. I am 90% confident that the true average loss in home value is contained in the interval. Yeah, then make sure, Meredith, though, I think you would. Make sure to, you might not have seen the numbers. Yeah, I think, Meredith, you got the 500 points for everyone right there. Make sure to then put the numbers in on the test. Yep. So if you put that as the answer for your test question, you should be good. And then just make sure to give the interval itself. But these are questions where people get to them on the final, and they say, I have no idea what I'm doing. I have no idea how to answer these. So we want to be able to do that. And yeah, so here's the interval. Let me see. I've got the upper. So there's the upper. And it wants the nearest whole dollar. Round to the nearest whole dollar is needed. So that's rounded down. And then the other one is 8942. Is that right? Because wouldn't the sense... Let me see this again. I think I wrote that wrong. I think it's 8943. I'm going to take it. 8943. I think I rounded wrong. Yep, I did. That's got it. And do you have interpretations that repeat the size of the sample? Well, it wouldn't be sample population, because remember, sample size is for a sample. Population is for everyone. So we sample population doesn't go together. Does that make sense, Meredith? Like the idea of a sample population is not true, or it's incoherent, because sample is a subset and population is the whole. So you could say you could include it there. It's not needed, but you could say from a sample of 33 bids, we estimated with 95% confidence the true mean loss in home value to be contained in an interval, blah, 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 blah. So you could mention it, that from a sample of 33 bids, we created a 95%, but that's not needed. It's not bad to say that, but we just make sure we get the necessary components. 1, what is the percent confidence? 2, what are we estimating? And 3 was the interval, which is lower and upper. So those are the 4 components you would need to properly interpret an interval. Yeah, so yeah, it's just, you could mention it, like from a sample size of 32 bids, we created a 90% confidence interval that estimated the true average home loss to be contained in the interval lower to upper. 8,942.54. That's what I did. I inverted those numbers. Yep, it should be 54. I was looking at the math as I was entering, and I was like, they shouldn't be the same, because if you subtract, just think about that, subtracting there, right there. I think we're gonna do Canvas content now, but really good work. And a lot of these questions are similar, but I do want to point to, so if you're still watching this last bit before we do go and do Canvas content, pretty much what it comes down to is knowing that a lot of our work right here, this one's easy. Degrees of freedom, is it? I can already see looking at it. Knowing that a lot of your questions really come down to what are we doing? What are we interpreting? What does this mean? Like, why are we doing this? So there's a lot of really good questions about like, what does this mean? What does margin of error mean? And the understanding is what is key, because if you understand how to solve these problems, they go a lot quicker. Let's go do the Canvas content. Okay, we're going to get some understanding right here on Canvas content. Okay. Canvas content. Which one are we on? Like number 7? Canvas content number... Let's do next week. Canvas content number 8. Hey, Marcus, good questions right here. Let's preview it. Let's do like 2 or 3 versions of it. Canvas content number 8. Okay. Let's see. Stat 201. Canvas content 8. Confidence intervals. Here we go. Let's do it. Okay. So whenever we do conditions for the rest of the semester, we have a thing we do in our class. We say condition 1, condition 2, and then we pause. But what are condition 1 and condition 2 always? What are condition 1 and condition 2 always? When we do condition 1, condition 2, they're always what? Which means they're required. Like you go condition 1, random, 10%, boom. Just you got those. So now you've narrowed it down to this or this. So here's the thing though. Now that you've narrowed it down to the 2 that it could be, because you know we always do random, means we take a random sample. We'd always do 10%, means we sample less than 10% of the population. That's an interesting math one. I could talk for 10 minutes on that, but just for the moment, we'll just say sample less than 10% of the population for reasons, because it creates undue error in the mathematics on finite populations. I'm gonna stop talking about that condition. How do we know the third condition? We always look at the type of data we're doing. So the third condition will be what kind of data are we working with? So tell me, if we're doing means, the data is what? If we're testing means, or making interval for means, cat or quant, right? So means are what? Cat or quant? They're quant. So now you don't see large enough n condition here, because large enough n has been wrapped up into not success failure, but nearly normal. Nearly normal means the shape of the distribution is basically a normal, and it can be checked with large enough n, checking a normal probability plot, looking at the histogram, or goodness of fit test. So there's 4 ways to check it. I could go into a lot more detail on that. We've kind of reviewed them with chapter 5 and also the large enough n condition. The 4 ways are, and I guess I'll show it really briefly right here. I think I've got some data. The 4 ways to check it are, I basically have it up right here from a previous question. 1, look at the histogram. We don't love looking at the histogram for the nearly normal because the bin widths can be very deceptive. Like you might think this is uniform, but it's due to the small bin widths. It is kind of normal, but just depends on how many bin widths you get that give you a different view on the shape. So looking at the histogram is usually not the best way to check things. A much better way number 2, is to look at the normal probability plot covered in chapter 5. The normal probability plot gives you a line which shows you what is normal or expected via the normal distribution, which has been overlaid onto this data. And you'll notice right here, the red line is where the normal's at, and here's where our data is at. These little lines on the outside are kind of your like lines, and you notice most of the data is inside the lines. So it's pretty normal. It follows the line pretty decently. Over here, we see a goodness of fit test, which was the 3rd way I mentioned. The 3rd way I mentioned is using the p-value on the goodness of fit test, and a high p-value on a goodness of fit test means that we still believe it's normal. That's because the null hypothesis is that the distribution is normal, and we failed to reject the null hypothesis with a p-value much higher than 0.05 for both of these tests, created by Shapiro-Wilk and Anderson-Darling, hence the names on the test for the goodness of fit to see if a distribution is normal or not normal. But to just contrast this really briefly right here, if you had data that looked like this right here, this is data I'm making that will be heavily skewed. Notice the numbers at the end. It starts off with low numbers. So we're going to get a right skewed distribution by making a graphic of this. So here you are with the right skew of the data. There's right skewed data. So you look at the histogram, you say it doesn't look that normal. Now we go and we make the normal probability plot right here called a normal quantile plot and jump. And if you notice, it doesn't follow the line. It actually goes outside of our lines. It goes outside here, goes outside here, goes outside here. Multiple points are outside our kind of, it's not that normal. Now, last but not least, we can do a continuous fit. You're not meant to do all this. You're meant to understand what we're doing, not meant to click all these buttons. So we go over here and we go to goodness of fit. And it says, we reject the null that it's normal. So this low p-value on a goodness of fit test, low p-value always means reject the null, p-value less than 0.05. If we have a low p-value, we reject the null, and the null was that the distribution is normal. So we reject the null that the distribution is normal, and we have evidence it's not normal. The last thing I mentioned, which is important to know also, is we used to talk about the large enough n condition. So the large enough n condition relates the following way. We have right here the we have the sampling distribution applet. It is possible that if the parent population is heavily skewed and we take a large enough sample, that via the large enough n, the distribution of means will be nearly normal. As the sample size increases, the distribution of the mean will be more normal, and that's what we're interested in analyzing. So for smaller samples, we're more concerned about this, but for larger samples, we can actually pass the nearly normal with the large enough n. You might be wondering, why didn't we do this to begin with? Well, the problem is right now we're doing data based on a sample. We don't know what the parent population looks like. In the previous chapter, chapter 13, sampling distributions of the sample mean, it would say things like the original distribution is heavily skewed. We don't know that up here now. We don't have access to that. We only have access to the sample data. So we could infer from a sample data set that is, and if we take a look right here, if we were to animate this, if we only had the sample data, we might be able to infer that it looks like the parent population is heavily skewed, but we don't know the parent population is heavily skewed. Especially for a smaller sample size, that would be a little bit iffy. Like if we only had 2 data points, we really wouldn't know this. And that's crazy. Those are 2, someone maybe sees that, wow. So 2 random data points just came from the very tail of this distribution. That's pretty crazy that we got something that far away, because 2 random data points are very unlikely to occur over there. We really just got one of the most rarest occurrence in that first observation. It was pretty cool what can happen with random data. So we don't know what the parent population looks like, and especially for smaller samples, we don't know, is this skewed? Is it uniform? So you have to watch out. That's why we don't use the large enough n, because we don't know the shape of the parent population. You can kind of use it if you have a larger sample size and infer the shape of the parent population due to evidence from a sample, which a sample size of 50 would probably give you enough information to infer a shape for a parent population. But really cool stuff right there, and that's a much bigger topic. Once again, all these ideas of what are these conditions, what do they mean, and how do they apply to us doing our work. And so here we are with a very good question. When doing a confidence interval for the mean, we use the following distribution to determine the number of standard errors needed for our confidence. Now be careful, this doesn't say standard deviations, and it says a confidence interval for the mean. So the answer actually lies in the work we were just previously doing, and also in the formula for the confidence interval for the mean. Which answer is it? Is it skewed, t, z, or chi-squared? So the formula sheet would be a huge help if you saw this on the test, because it says confidence interval for the mean. I'll show the answer here in a moment, which will give away the answer. But is it skewed, t, z, or chi-squared? Skewed, t, z, or chi-squared? Which one of those would it be? So remember, if you were stuck on this, it's t, Marcus, exactly. And because it's a t interval. And I think the formula sheet even says it. So we were just doing a previous problem. Great job, Meredith, there. And think about what you would use to estimate the true mean. What is your best guess of the true mean? your best guess of the true mean. Like if someone had to guess what the true average loss was. Hey, Jesse, good to see you here. The best guess of the true mean would be the what mean, which is why it's the center of the interval and why we use it to make a confidence interval. The best guess of the true mean would be the what. Like if you had to guess the true average loss, your best guess would be the sample mean. Boom, Marcus, you're seeing it. So this is why this is called the estimate. And then after the estimate, we give a margin of error. So we have an estimate and then we have a margin of error. And the estimate comes from the sample. So the sample is where the estimate is. And that's also the center of the interval. Lots of different words to talk about it, like the sample, and Jesse has right there. The sample creates the estimate, and so the sample mean is the best estimate of the true mean to create a confidence interval to estimate the true mean. And if you're wondering why it's t, we use the t here thanks to William Gossett. Check out those stories earlier, and that confirms it is a t distribution right there. Review question right here. We've done this one a lot. This is I hope you get this question on the test. The success failure condition for confidence intervals for proportions says you need what? At least or at most? Do you want at least 10 successes, at least 10 failures, or at most 10 successes, at most 10 failures? At least 10 successes. And if you don't meet the conditions, what happens to your distribution? If you don't meet the conditions where you only maybe have one expected success, your distributions will not look what? The whole point of meeting these things is to use the basically what? Like if you meet the conditions, you can use the distributions we use because this is not normal, right? And don't be careful. Don't think nearly normal on this because that's for means, but you want at least 10 successes, at least 10 failures. And when you achieve that, this is the expected amount of successes. It is the mean of the distribution. Watch out. And yeah, if we don't have at least 10 successes, at least 10 failures, we won't get this normal shape to the distribution. It's technically the binomial, but it does apply to the same concepts of successes and failures. Tell me really quickly, how many expected successes would I have from this data right here? If I tell you that 40% of students own a pet and I talk to 50 students, so there's P and there's N, if 40% of students own a pet and I talk to 50 students, how many expected students to own a pet? How many students would you expect to own a pet? Which is expected successes. This is what it means. And you see it looks normal. 20. So how many do you expect to not own a pet, which is NQ? And we will use NP hat, NQ hat, but this is kind of showing the same sort of work. How many do you expect to not own a pet? 30. And notice that adds to 50. Like I expect 20 to own a pet, 30 to not own a pet. So you could also check it with the NQ over there, but that's like the distribution of students expected to not own a pet. Remember, the amount of successes, amount of failures will always be some amount out of the total sample size to add up to the complete sample size. Just kind of some quick practice and checks on those to make sure we kind of understand what's going on. Good stuff. At least 10 successes, at least 10 failures. Decreasing the sample size will make the margin of error a smaller value. Now, let's not even think about this mathematically for a moment. Let's just think about it conceptually. Margin of error is an amount of what you have in your estimate. Margin of error is an amount, think of a U word, like margin of error is an amount of what, like here's my estimate, and then here's a margin of error. So we go margin of error minus plus margin of error. Unknown uncertainty. I like to say uncertainty. Like you're like imagine I tell you, hey, let's go get a steak. This steak will cost $40, but I could be off by about $10, right? So the steak is probably going to cost somewhere between what and what. If I tell you, yeah, the steak at the restaurant is usually about $40, but I don't know, they changed the price. It could vary by about $10. So the steak is probably going to be between what and what? Because that's my margin of error. I'm like, well, last I checked it was 40, but they changed the price on the market value. So it could be differing by $10-ish, 30 to 50. Yep. So I just gave you like my uncertainty in the price of a steak. Does that make sense? Like, I don't know, I could be off by about 10. And so with this right here, when do you think Brian would have a tighter interval? Brian would have a larger amount of uncertainty if he went to the restaurant more or less. So let's say Brian's only been to the restaurant one time, or Brian's been to the restaurant 100 times. When would Brian have more uncertainty in his estimate of what the steak costs? Just think conceptually. So, hold on a tag, right? So when would I be more uncertain about the price of the steak? If I've been to the restaurant, what? I'd be more uncertain about the price of the steak if I've been to the restaurant. What? I want someone to be like, I see it. I'd be more uncertain about the price of the steak if I've been to the restaurant. What? Only think conceptually. Yes. If I've only been one time, right? Fewer times. So now let's look at it mathematically. Here's how it mathematically works out. So we understand conceptually, like we'd be more uncertain with less samples. More uncertain means larger margin of error. So in a confidence interval right here, we see that the margin of error component is all right here. Everything after the plus or minus is the margin of error. And so we are dividing by n. So since we are dividing by n, if n decreases, then what? For smaller n's, this quantity will be bigger. And if this quantity is bigger, because it's a smaller number on the bottom, then that would make margin of error bigger. Does that make sense? And you can plug in numbers right here to check your work, but just think about if you plug in like s over square root of 1 versus s over square root of 100. So what happens is, since you're dividing by, and just think dividing by a bigger number will make this quantity water. Like if you're just trying to remember it, dividing by a bigger number will make this quantity water. Dividing by a bigger number, like just even ignore the square root right there. Just think of it as n. It's not n, it's square root of n. But just dividing by a bigger number will make that quantity smaller. It is square root of n, but just conceptually speaking, it might just be like, oh, we're just dividing by a bigger n. So with this right here, we see it mathematically now. So I think we basically got it. Decreasing the sample size will make the margin of error smaller. No, decreasing the sample size will give us more uncertainty. It'll make the margin of error wider. Like if you have a smaller sample, you would not have a smaller margin of error. You would have a, which we just saw. And we can get the next one pretty quickly too. Larger margin of error. So this is false. But with this one, wider interval, right? Wider interval, larger margin of error. Great job, Meredith. Great work there. We'll do another version of this, and great work. These are good conceptual stuff. The only way to change the margin of error is to change the sample size. Really love this question because we just covered it. We can change the sample size, but what else can we change? This is the margin of error in purple right there. We can change the sample size. That'll, if we collect more data, smaller margin of error. Hey, Sloan, good to see you here. We got the cowboy hat, we got the Giga Maggies on right there. What else could we change? Confidence, yep. So if I told you, like, let's say you're like, and this is a steak dinner at this restaurant, and I said, I am 99% confident that the steak dinner will be between $30 to $50. And you're like, so I'm okay to bring $50? Would you feel pretty safe if I said I am 99% confident that the price of your steak dinner will be between $30 to $50, the true price of your steak dinner, with tax, with tip, with everything? I'm 99% confident. And so you grab a $50 bill off the table because you might get some change or whatever. This is with tax, with tip, with everything, right? So you'd feel good. But if I only gave you a 10% confidence interval, which we usually don't make, well, the center would still be the same, but a 10% confidence interval would have a much smaller margin of error. Just theoretically. This is all just theoretical ideas. Ooh, not 52, 42. Margin of error's got to be symmetric, plus or minus 2. But now I could say something like, I'm 10% confident that the price of the steak will be between 38 to 42. Does that make sense? Like, I'm only 10% confident. I mean, it could be in that interval, but the true price of your steak dinner, but I don't have as much confidence as I do in this 99% confidence interval. And mathematically speaking, this is changing the T right here. And if you do more confident, then you get a larger margin of error. So if you look at the blue arrows here, they represent that when you get a smaller, we've connected here, larger T statistic is going to create a higher margin of error because it's more confident. And a smaller n is going to create a larger margin of error. Sorry about that. So n is inversely related to margin of error, and t is positively related to margin of error right there. Good stuff. Really good work. And we'll do one more version of the Canvas content. Did anyone get 100 on the Canvas content already? So the only way to change, no, we can change the percent confidence of the interval. Uh-oh. How'd I get this wrong? I see it. Did review what I said. I was too much in review mode. I got caught with a classic thing that they say don't do on tests when making tests. And why is it success failure? And why is it success failure? Meredith, 500 points. Meredith correcting Brian right there. It says not a requirement. It says not a requirement. So I kept talking about how the success failure is the requirement. And it said what is not the requirement. Hopefully someone's watching the full video. I am working through these, explaining these. So you got to catch those little things that Brian doesn't read is not a requirement for testing means or for confidence intervals for means. The nearly normal is the requirement. So I guess because we needed 4 choices, so then we did not. My hair's looking all crazy. That's what I'm going to talk about right now. Let's do another version of this and we'll get that 100. We get 2 attempts. I'm just showing you get your 2 attempts. No matter what the shape of the parent population is, as long as our sample size is 10, we can conclude that the sampling distribution of the sample mean is approximately normal, or that we meet the large enough n condition. True or false? No matter the shape, we can conclude that it's nearly normal with at least 10. No. The numbers are 1, 25, and 100, and we would need a larger sample size the more skewed it is. So large enough n right there still comes into play, which is very important. We could deduce from the sample a decent understanding if we have a large enough sample size to kind of understand what's going on with the shape. So this is false. Which of these is not a requirement for testing means? Success failure. That's only for proportions. We need at least 10 successes, at least 10 failures. I do like this one. Don't even read the answers. A confidence interval is made from a what to estimate the what for a what. Well, this is a good phrase to know. We always make a confidence interval from a what, and you can see it in the formula. We make a confidence interval from a what. Now that's a mean one of these. We always make a confidence interval from a what? Well, this is not a parameter though. Parameters are for populations. So we say sample statistics give us estimates of population parameters. So the confidence interval is made from a sample, and there's a sample mean right here. So that is going to create the interval. So the sample creates the interval. So a sample statistic creates the interval. And that gives us an estimate of the population. And so the deal is, so it's the sample mean. So sample mean, and that's a statistic, is an estimate of the true mean, which is a parameter. The true mean right there. So the true mean is a parameter for a population right there, the truth for all. So this is going to be, the confidence interval is made from a sample to estimate the truth for a population right there. Good stuff. So this one, I love these questions. This is one of my favorite ones because I think you know how to solve this. People get to this question on the test and they're like, I got no idea. Yeah, that's why we come to, that's why we practice, Sloan. You got it right there, 100 points. You know what's up. We're here to practice. So with this question right here, people get stuck on it because the numbers are a little bit weird. But I don't want you to look at their numbers. I want you to think this over. And I want you to remember how to solve this. We're learning how to solve things, not solving just this one question. If I tell you, I think your test grade will be somewhere between 70 to 100, I'd be pretty happy with that. The estimate of your test grade would be. So we're doing a fake question right here to learn how to do this question. So I tell you, Brian estimates your test grade to be between 70 to 100. What is his estimate? What is his margin of error? Good to see here, Vincent. So this will help us solve this question with easier numbers, and then we can see how to solve it. So what is his estimate? Well, I estimate between 70 to 100, but what did I guess? Marcus has already got it. Great job, Marcus, right there. So the estimate is always where. Marcus notices this and sees this, that the estimate is always at the where of the interval. So the estimate, the best guess, the estimate is always the center of the interval. So it's the center of the interval. Now, if we were to write an equation for this, we could do upper plus lower divided by 2. It's one of the equations to do it because that's just averaging the numbers, right? So if we do this right here, it's 70 plus 100. And don't memorize the equation. Think about why you're doing this. What am I doing right here? I'm just averaging the two numbers. Does that make sense? Like conceptually, once again, don't think about memorizing it. If you understand why you're doing it, you'll remember how to do it and not memorizing a formula like, oh, the center of the interval is just the middle. And so you just average the numbers together to find the center. So now that we know this, we can oftentimes figure out the margin of error. But the margin of error has another concept with it too. The margin of error is always what the length of the interval. So if you think about the margin of error here, I wish I'd drawn it a little more symmetric because it is symmetric. Much better. The margin of error is always what the length. So here's the length of the interval. This is the length of the interval. And here's the margin of error. It's always half the length. So, or if you do 2 times the margin of error is the total length, Meredith. So a lot of ways to think about it. And so with this right here, how would you find out the length of the interval? To find out the length of the interval, what would you do? How would you find out how long this interval is? Just think conceptually. To find the length of the interval, you should just do what right here? Remember, we're trying to understand it conceptually so we could solve any problem. To find the length of the interval, you should just do what? I mean, we got 2 numbers right here, right? We got this number, we got this number. We want to find out the length. Meredith has the answer right there. Yep. Just do, you can actually, Caitlin, that is, we're throwing Caitlin another 100 points. Caitlin, that will get you the answer. We don't have that information for this problem, but Caitlin has shown how we could put a question that would not give you the same information. And Caitlin said a alternative formula worth another 100 points. Caitlin gave the alternative of center minus lower equals ME. So Caitlin's just finding the distance right here. Great work, Caitlin. Also, you could do upper minus center. And that would also be the value of this right here. But then also the classic way we do it is take half the length of the interval, which is upper minus lower, divide by 2. And for us, that is 100 minus 70, divide by 2 equals 15, because that's half the length of the interval. So once again, we're learning what it means, what the margin of error is. It's half the length of the interval. The estimate is at the center of the interval, and you can see this with any of the formulas we've been practicing over here with the estimate, which this is the center right here. And then the plus or minus always leads to the margin of error right there. Okay, so all we have to do is find what for this question on the screen. Just find half the length of the interval. Okay, for the length, we do the upper minus the lower, divide by 2, and there's the answer. Round to 1 decimal, submit quiz. As long as I didn't put an error in, we should be good to go. Second try, 10 out of 10. So hopefully we have some 10 out of 10 hundreds. We'll do one more quick version, see if there's anything else new. And we'll just kind of speed run it here to see what we can do. So preview the quiz. Okay. Which of the following would you not use to check the nearly normal? Bar charts are for categorical data, histograms, normal probability plots, goodness of fit tests. Check out the first version we did of this at the very start of the video. I went over all of those, and that would answer this question right here. Never mentioned bar charts because those are categorical. An employee at the Guinness Beer Company invented the student T. Yes, he did. That is William Gossett, who invented the student T distribution while working at Guinness Beer. We wanted at least 10 successes, at least 10 failures. Take half the length of this interval. I'm going to estimate in my head. That is 8.8, I believe. No. It's 7.8. 7.8 divided by 2 is 3.9. We're guessing. Let's see if we get it right. Decreasing the sample size will make the margin of error smaller. No, it'll make it larger. That is false. Kind of did it really quick right there. Did we get that 10 out of 10? Yep, we did. Good to go. Practice it. Practice makes perfect. Just understand why you're solving them. Like if you're doing this for the test, you could come back to this and review the concepts we've done right here with things like margin of error to better understand them. What other questions are there? Sometimes we do a speed run for fun just to see how fast we can get it. We got 2 10 out of 10s out of 3 attempts. We messed up a not question early on, but it happens every once in a while. What other questions are there? What do we have? It's all about that practice. What other questions do we have? Let's see right here. Any emails? The emails. Information, literacy, and curriculum. Oh, I can buy a book or something. I can buy a book? Let's see. I had a question about data analytics executive summary. I had a question about knowing which distribution is normal based on sample size. Which one is it? Which one is that, Marcus? Yeah, here we'll talk about that. So, and let me reference that video because I think we did a good job in that video. But let's go do data analytics 6. Which one are you wondering about, Marcus? Is it a specific? Is it a general question or is it a specific one? Like, is it like in general knowing things are normal? I got a billion tabs open. Oh my gosh, so many tabs. Closing all the tabs here. Let's see. Let's go get that assignment. Data analytics. Yeah, good questions, Marcus. Looking at histograms, at what sample size would you be comfortable using the normal model as an approximation for the sample? See, wait, is that in chapter 14? I need to go and change up. Where has Terry posted the? Let's see, might be like review videos to come. Dang it, the review videos are posted. I don't know why sampling distribution is put on. It was asked on 14. I probably need to clean up the assignments as we do class. That's all sampling distribution stuff. It's probably like 5 or 10. You have to look at the histograms. I probably need to eliminate those questions. I do not know why that's in the assignment because those are sampling distribution questions for chapter 14, the other chapter. So the book used to do confidence intervals and sampling distributions as their own chapter, but we prefer to do sampling distributions as their own ideas and then confidence intervals as their own ideas. But they do sampling distribution of the sample proportion and confidence intervals for the sample for the true proportion in one chapter now, chapter 13, and then they do sampling distribution and sample mean and confidence intervals for the mean in one chapter. I guess they didn't want too many chapters, or they just reorganized their book in their latest redo of it. And it's a little confusing to sampling distribution and sampling and confidence intervals are two different ideas. So we decided it was a better format, which then makes the numbering of the chapters just confusing. So, darn chapter numbers. That's why there's chapter 13 on test 2 and chapter 13 on test 3. Confusing. Data analytics. Wait, wrong data analytics. Data analytics. Wait, let me find it. Chill music. Here it is. Next Wednesday, week from today. Okay. We've got the files. Okay. Well, let me fix this link. Let me just put the files in here. Doing some background work right now, Sloan. I'm just gonna go grab the files. I don't know what download the files. Well, maybe it's good. People go to the site. I'm just gonna leave it. Yep, there's the files. Yep. I don't know why we did it that way. I don't know. Okay, here we go. Let's do it. Okay, we're doing the data analytics here. And with the data analytics, the number one thing I ask people to do is to look at the rubric. If you are watching this video now, do not start writing anything till you read the rubric. Data analytics 6, executive summary. And this is what I beg of you also. Do not send your work to anybody. Do not receive work from anybody. If you find things on a GroupMe or find anything is on any site online, do not use it. Maybe tell us that's your call. I prefer you tell us because that's huge problems and a lot of people get in trouble, especially on this one because this one's mostly writing. Yeah, so read the rubric. Don't take anyone's work. You could get in big trouble. Don't send anyone your work. Your friend calls you last moment and says, hey, I'm stuck. Can you please just email it to me? I swear I'm just going to look it over. Don't worry. I'm going to look over it. Don't send anyone your work. Big way to get in trouble. Okay. I just hate having to do the student conduct reports. Like it's 2 to 3 hours of my life that I just don't like spending doing it. So be nice to Brian. Don't make Brian do student conduct reports. So with that said, here we are. Here is the rubric. On the rubric, you will be doing an executive summary. You'll be doing future research. And then you also have, well, I think Terry has basically like, here we go, the format right here, all this stuff. I want you to read over exactly what you'll be graded on. Notice that you want to be always where they will click this button. The graders literally click these buttons. They click this button if you got all the credit here. They click this button if you got all the credit here. They click this button here. You get the theme. So with this in mind, the executive summary is going to start with the reason why. Now, what is the reason why? Well, we're going to go here. This part of the executive summary should orient the reader to who the company is, what they are researching, and why they are researching it. So who is the company? What are they researching? And why are they researching it? Now, how would you know any of this? To know any of this, and I'm not going to do any of the project here, but I want you to think it over. We're going to go right here and open it up right here, and we're going to go right here to the body of the report. Instructions are basically the same thing, but this is the report right here for you. So you need to look through this report right here. It does not have an executive summary on it. So here's the report. I'm not reading any of it. The histogram shows the tip distribution within the salon. So here we go. Here's all the data, all this stuff right here. You can see the report. So what you need to do is you've got a 6-page report right here with a scatter plot, with some more scatter plots. There's a regression analysis. You've got a pivot chart right here. You've got an analysis of the difference between the two distributions for card or cash. You've got a mosaic plot showing people who are not married versus married if they use cash or card. You've got a pie chart right here showing what days of the week people came in on, and also the bar chart. So pie chart and bar chart showing days of the week people came in on. And you've got just some extra information right here on the distribution of tip amounts. So thinking about all of this right here, we got to make some new levels, Jesse. Got to get some even higher. We got to get to that 1.3 bonus points. So all of this right here, you can see it relates to a salon. I think I can say that. You can see the different things that were analyzed, and you want to then look at what they learned. Now, one thing I want to point out right here, because we're only talking about like, you want to think who the report is, why they're doing this report, and what they're interested in understanding. You want to read the report. Just read through it. It should take maybe 5-10 minutes to read through it. This is an example of when we are building our big Stats 1 project. Yes, exactly. This is what you will be doing for your project, but you will also put on an executive summary and a future research. That is what is missing from this report. So an executive summary, the full thing, which we're going to talk more about the next component about it, is the full report. Now, I know this is going to sound crazy. Why would the executives want an executive summary? Just think, you're an executive, someone hands you a 6-page report. Why do you want an executive summary? Think why it's called an executive summary, and think of it like as a Cliff Notes. Like, why do you want an executive summary? Like, you're an executive, someone says, here's a 6-page report, and you say, where's the executive summary? Top level quick read, exactly. So it's going to have all the important stuff, right? It's going to be none of the fluff. And Meredith, exactly right there, provides an overview of the main points of a larger report. Exactly. That might have been from Google or something. So we need to make sure we start with like, who are we? What are we doing? And why are we doing this? Look to the rubric to directly think, how am I going to get my points? Am I directly saying at the start of my executive summary, outlines what is being researched? Boom. Make sure that is done. And then we have right here, we have who the company is. Who is the company? What they are researching and why they are researching it. Very important right there. Be very clear, be very direct. I'd probably spend about 3 sentences on that. 3 good, strong sentences on it. Next, we have key findings. And I want to point to where people make mistakes here. Rarely, and I really don't like, just pointing out, I don't like that there's too many results given. That's usually not the problem. Usually the problem is students don't give numeric backing when they give their results. So when students give results, you need to give numeric backing. We should see numeric backing right here. Boom. With numeric backing. What is numeric backing? Numeric backing literally means citing the numbers. Now, here's the thing though, and I think this is a good point. Are you going to give every single number throughout the whole report? Are you going to give every single number that everyone could see in the whole report as a whole report? Think what you're creating. You're creating an executive summary. Exactly. No way. You're going to talk about the most important things that are most important to the salon with their objectives. The key ones. Exactly. What do you think is most important? And don't worry, we're not, I mean, if you think the grader's mean, just tell me. But you want to find the ones you think are most important and then cite the data, cite the numbers, and make it very clear as you go through and find out what you are going to summarize. Now, don't just take sentences like this, kind of read it, take it in, and then, like, that's a possible thing you could talk about. And then think about what's most important and then reinterpret it. You don't want to just take a sentence right here and copy paste it. You want to summarize the report, not just copy paste from the report. So usually you could lose points if you just copy sentences and bring them up and just copy paste, copy paste. That's not really summarizing a report. That's just condensing a report, which a summary kind of does. But you want to find the way to explain it in your summary written by you. So with this next, we have the action item. What is an action item? The action item is going to be what you are telling the company we should do. And basically, and I just talked to someone about business analytics, do you think there is any format really for companies? If you work for a company, like let's say you work for Clayton Homes, Pilot, maybe I shouldn't because I've never worked for them, or Pepsi or Kroger, they've got dunnhumby. Do you think there's like an exact format for how you have to write an email? I mean, they might have preferred things. They probably prefer certain grammar, but do you think there's MLA, APA? Do you think they say, oh, your emails were not in MLA format? It's not really the way the business world operates. From what I've seen, did an internship at 3M, worked for other companies, I guess going further back, but they're not really focused on like MLA. They usually want you to be professional, courteous, and to the point. So, which I'm usually more flowery with my language. But with this, the action item is saying what we should do. So you should be very what in your suggestions for this company. Your suggestions and a suggested course of action, I would try to like lay out a plan. It doesn't have to be like a big in-depth plan, but be very what in what you're telling. Direct and concise, Meredith. Exactly. Like, and think about it. It needs to be connected to the data. Like there should be some logical reasoning. If you're like, we should close the salon and make it a donut shop, you're like, what data do we have to back this? This is why you're giving the numeric backing, which is going to lead to what we're going to do. So I would probably, like, if you think about your format right here, 3 sentences up here, 4 sentences here, maybe 2 sentences here for a total of 9 sentences. I know it says 5 to 8 right there, but I always like to err on the side of like a little extra right there. Clear and concise, approximately between 5 to 8 sentences in paragraph format. And that's 2 points right there for being clear and concise and doing. If they were to take off for having an extra sentence, sometimes they're great. Every once in a while, I get a grader who's a little too harsh. Written in a way that makes it hard for the reader to understand. Yeah, they shouldn't. That should be only clicked if it doesn't make sense. Don't expect many people to lose points here. You could maybe, it should have like too short also, but yeah. Now this is where people usually get a little bit confused because this is 5 more points. 5 more points right here on future research. So future research is something that goes beyond the report that was currently done and is new ideas. Exactly what it says right there. So when you think about future research, I want you to think about why you would not re-go through your report. The executive summary summarizes the report. The report is the report. So why in your future research section would you not just go through the report again? I think we give a format of how to turn this in on the following page right here. So here's your format for turning it in. Why in your future research section would you not? You need to be creative, exactly. And think about this, when you have this, your report is going to look the following way. Your report is going to be an executive summary. And then, can I copy paste the report? Here's what it's going to look like on the overview. So you have an executive summary. Let me make this bigger font. report's not that many pages. So here's what it looks like. You have your report right here. Report right here. So your executive summary is the summary of the report. Could be a little bigger, maybe a longer report. Why would you not just use the future research and say, well, we found this, we found this, we found this, and why is the future research going to be new ideas? Because the executive summary is the shortened version of your report, and then the report is the report. If we were to go back through the same ideas, well, they've already read the condensed version of the report, like the one pager right here, and then the report is the report. You've never seen it before from the scene. Well, that's the way to think about it, is like the future research is its own standalone thing, not connected to, I mean, it should be connected in a way. Like, you're not going to say, once again, we need to do research on donut shops. I just want donuts, apparently. You're going to somehow come up with things that are new ideas that this salon has not looked into. So you wouldn't go back through and summarize the report because you've already done all that. You need to be creative now. You're telling the company, here's things we could do that, not like what we will do from the report, but kind of new ideas to go into that we haven't even explored yet. So very important to understand that the future research is a new pathway for us to analyze and look at. And here we are over here. So future research is clear as where to proceed and also connected to report. So once again, by connected to report, we're meaning like, and I don't want to give ideas because I don't want to wreck your creativity, but let's say Brian has a video game shop and I'm analyzing what video games people are buying. Well, maybe we didn't analyze, the retro market. So I could say none of the analysis in this report. See, now everyone's going to say none of the analysis. Every time I say a phrase, I'm like, no, that phrase is going to appear in like every single project, every single future research. But I could talk about how, things we could do. It's not that we are making decisions on this. It's ideas of what we can think about and start to collect more data on. That's a good way of thinking about it. Does that make sense? It's not what the company's going to do from what we found. That will go where. What the company's going to do from what we found is going to be in the what format. From what we learned in this report, what we are going to do is found where, in the where. From what we learned in this report, what we're going to do is the executive summary and is the action item. Does that make sense? No, it's that I'm too afraid of Sloan, because I don't want anyone to be like, because every once in a while someone's like, I've seen reports with like 95% matches, and then some people have said like, oh, I just went to office hours and wrote what you wrote. But the thing is when you have a 95% match and then the next highest projects are like 30% matches, people don't usually match 95% of the phrases. I know, right? And so please just don't say anyone your work. It's not fun for us. And then so the future research is kind of things that expand upon what we've already done, not like the company should be doing this like because of the data, but things we haven't considered that are kind of new avenues for us to pursue. And so think about that like with my retro game store, with my game store having not even considered the retro market. Like that's something we didn't even collect data on it. Like, so let me tell you this. So is my company, my game store, going to make decisions on the retro market right now? Is my game store going to make decisions on the retro market right now? Would we make decisions on what we're going to do? Would we have an action item on the retro market? Would we have an action item like, we need to do this on the retro market? Would we have an action item on the retro market right now? Like, we need to make these decisions financially on the retro market. I think this might help clarify. And the answer is no. Why would we not have any action items on the retro market? It's future research. We don't know what, we don't understand it yet. Does that make sense? Like, we haven't looked into that yet. It's not in the report. It's connected to my game store because my game store hasn't currently considered that. Does that make sense how this is future research? We don't have an action item on the retro market because we haven't looked into it. And so if we haven't looked into it and we don't have data, we need to do future research on that. So it is kind of, if you think of it as an action item, but it's not like we are going to maybe do something, maybe pursue this, but it's not that we are going to make a financial decision or make changes to the company yet. Like, we're not going to change what we're doing. We're not going to increase our retro market because we don't know the data yet. And then the clear, concise, once again, 5 through 8 sentences. If you're good on that and you're clear, but you just want to make sure you expand upon these things and you use your creativity, like me talking about my game store, possibly looking into the retro market. I could even Google some data on that and talk about the increase in sales and all these different things. Dang it, I'm like I have more. I literally had another idea in that moment, but if I say it, I think I'll see too many reports that say, like, maybe we could do this. Find a good way to put it in a business format. I was thinking about like hosting local speed. You see, now everyone's gonna say we could host local whatever. No, but we need to look at that market though. We need to understand it, and that's a little. Almost doing an action item right there, which you have to watch. You don't want to give a financial decision for the company, so be careful on giving a financial decision that would cost money. I mean, time and money are they are one and the same at times. But you might want to explore or look into certain things to see if there's viability and collect data. Think of this more as collecting data and understanding more things before making decisions. Does that make more sense, Sloan, right there? Hopefully this we kind of went through it last week, but we have the information posted and there should be some understanding, I hope, now of what you're expected to do. And this goes over it more in depth. But I think, once again, the rubric is the huge key to understanding what you're doing. Like, if you understand the rubric, you should understand what you're doing. You didn't hear anything. Yep. What else do we have right now? We'll be doing a lot of work in class, but yeah, we've only done a few questions today. Awesome. See, chapter 14 quiz. Yeah, sure, of course. Let's do some chapter 14 quiz. Okay. Which one should we do, Jesse? Here we go. Chapter 14 quiz. Okay. These are some of our favorites right here. We love these ones. 99. This one's tough, though. That one is tough to get. No, it goes below at that point. That first one. First one's hard to guess. It's even further, isn't it? Yeah, let's find it. Which one should we do on chapter 14, Jesse? We need the apps for this. That first one, because of the high degrees of freedom, is very hard to guess. So when we go to the T distribution here, or the low degrees of freedom, I misspoke. Software analysis, yeah, let's do that one here. 26 degrees of freedom, 99% confidence. 26 degrees of freedom, 99% confidence, 2.78. What was my first guess on that? Ooh, look at that. First guess was pretty close, and I missed it as it went up. Okay, let's look at software analysis of the salaries of a random sample. Software analysis. Does it give data or summary statistics? Hot dog lab one. Does it give data or summary statistics? What does it give? Because it might be a jump version. Software analysis. Where is it? Aha. Oh, it gives the interval. It literally gives the interval. So they're trying to estimate the true mean of something right there. Looks like an interpretation question. Okay, software analysis. It's an interpretation one. So it's not a compute the answer one. Oh, good. Go away. Quiz. And let's mark the question. Oh, someone's got one too here. We'll do one next one. Stat 201, chapter 14, quiz, software analysis. Okay. Now that let's go using the TI. Yeah. Oh yeah, one prop Z int. And I've got a full playlist on this too, Sloan. I'll find it for you in a moment, but go to the playlist on the channel, the TI playlist. I've got a full playlist showing how to use the TI calculator for these. But then remember, sometimes you're given a question that you have to know conceptually. This is the lower and this is the upper to estimate the true mean of tech pay right there. Yay, Sloan, you rock right there. And I made them concise and quick videos. Also tried looking some of those up in your past videos and I couldn't find any. Are these new questions? Yeah, sometimes they are. So this might be a new one that I haven't done before. It's all conceptual, it looks like. So let's see what they're asking. Now, once again, we want to interpret this, interpret our interval. So we would say, I am 90% confident that the true mean of tech pay, see how that even is the true mean of tech pay right there? It literally has. I am 90% confident that the true mean of tech pay is contained in the interval lower to upper. If many random samples of 288 teachers from Nevada were taken, about 9 out of 10 of them would produce this confidence interval. No. The wrong interpretations are just crazy sometimes. About 9 out of 10 confidence intervals will... So about 9 out of 10 intervals... No. About 9 out of 10 intervals will produce a confidence interval that over... No. This one's probably going to be correct. This conclusion is incorrect. About 9 out of 10 intervals will contain the true mean. That's correct. About 90% of the intervals will contain the true mean. But different samples of 280 teachers will produce different confidence intervals. Yeah. It's a very weird, bad interpretation that they give right here. But what we're saying is 90% of the intervals will contain the true mean in the long run if many intervals were created. And that goes back to the idea of it's not one interval containing the truth. It's about the repeated process of creating intervals. We have a slide over it, and I've shown the applet N is sent out multiple times about how when we do, well, there's the William Gosser right there. When we do intervals, it's not about one interval. Where's the slide on it? Here it is. It's not about one interval containing the truth. There's the true proportion, and here's our estimate from a sample, and the true proportion is contained in 95% of 95% confidence intervals, like the true mean would be contained in 90% of 90% confidence intervals. If many random samples of teachers from Nevada were taken, about 9 out of 10 of them would produce a confidence interval that contains the mean salary of all teachers from Nevada. The way they word these. Oof. Okay. Which one do you think right here, Jesse? Let's read over them. This conclusion is incorrect. All 10, well, that's just dramatically wrong. No, 90% of the intervals. This conclusion is incorrect. About 9 out of 10 intervals will produce a confidence interval that, no. This is incorrect. About 9 out of 10 teachers surveyed will earn a salary within the interval. So frankly, what they're doing here in this one is they're actually phrasing the previous one correctly. If many random samples, which is what the slide shows, that's this slide, many random samples are taken. That's a random sample, 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 that's a random sample. If many random samples are taken, then what we will see, about 9 out of 10 of them will produce an interval that contains the true mean salary. And I do want to show this again because huge shout out to Enes. So this one is correct. And Enes sent this out right here. Enes sent out a demo, which is really excellent, showing this. So we're doing 90% confidence intervals for the true mean, which is literally what this shows. So, and it said samples of 25, I think. So here's normal. And we can raise the N up to 25, I think they said. So if we take, here's the true mean right there, the mu. If we take many random samples, here's a random sample, there's a random sample. That one did not contain it. You notice right now only about 71 or 80% of the intervals contain the truth, but many random samples are going to show us that over time, that many random samples, the repeated processing random samples, 90% of those intervals will contain the truth. We'll leave this running in the background and we'll come back to it because we need to let the law of large numbers come into play because every once in a while we get an interval that does not contain the truth, as in the truth, the mu right here is outside the interval, like it was for that interval. So we'll let that run in the background right here. It was 288, so we were taking larger samples. Sample size right there doesn't matter, but it's relative to this example. About 9 out of 10 teachers from Alabama. No, this is to estimate the mean, not an individual. And I think that right there is illustrated right there. The interval is for the population mean salary, not for an individual teacher's salary. About 9 out of 10 of the teachers surveyed earned between this. No. The interval, I think we might just repeat this again. The interval is for the population mean, not for the salary of individual teachers. I mean, that is true. It's not for the sample mean, and this is also not correct. The interval for the, no. The interval means that no, not a single right there. And then we got, is the hot dog question? No, that's not the hot dog, that's the body temperature. Hot dog question is the classic one. It's been around for a long time. We are 90% confident that the average teacher salary in the just when you read that right there, that goes outside the scope of the data they collected. The entire country. No. Our sample has to be representative of the population we want to understand. So, not from the state right there, out of the scope, yeah. So great job, Jesse. Yep, the conclusion is incorrect. The confidence interval only addresses the teachers in Nevada. We should have everything correct. I usually like to do a double check, especially on the wording ones. And now take a look. We've let the law of large numbers come. What? That's weird that does that. It's at 92%. I don't know if it did something weird when I closed the app for a moment, but the more I let this go, it's going to approach 90%. I know it's above 90% right now, but once again, this is just the law of large numbers needs to come into effect, that we let this simulation go even longer. I don't know if it acts weird when I have it minimized, but it should just still be running the simulation in the background when I have it minimized. We'll come back to it after the next question right here, and we'll see that it is approaching 90% because the law of large numbers is an amazing law. A researcher measured body temperatures. So a researcher measured body temperatures. They measured waist sizes. That is a sampling distribution question. There's the hot dog question right there. Classic question. Oh, there it was. Body temperatures. Okay, so for this one, we are seeing right here jump data. Sample size doesn't matter. Depends on how you say that. How much the percent we sample from a population doesn't matter as long as it's less than 10%. The sample size does matter. It does make the margin of error smaller for a confidence interval. On your, so yes, the sample size to show that 90% confidence intervals work doesn't matter right there. Good questions, Meredith, 500 points. It wouldn't matter that they took a larger sample. It still holds true that 90% of 90% confidence intervals in the long run will contain the truth. Good question, Meredith. In the simulation, it always holds true that 90% of 90% confidence intervals will contain the truth, and the sample size is not part of that understanding of how they work theoretically. And so we'll see it approach it as we just let the simulation run. And so with this right here, we have a sample of 52 data points. We get summary statistics. So this is a really good question right here because we're not using software to find the answer. We're actually going to solve it ourselves. So also for, mean cholesterol. So what should you do to practice if you get data like this? What should you do to practice if you get data like this? You should immediately do what?
Notation, brother.
We need to mark our notation. There's only really 3 things in here we have to mark. Annotate that notation. So what should we mark right here notation-wise? What should we mark? They counted 32 people? You got it, Jesse. So this is n equals 52, count of observations. Sometimes there's a difference on the wording, so you have to understand that count means the count of observations, like how many people did we observe. The standard deviation is going to be S, and then the mean is going to be Y bar. Why is it not mu? It's not mu because we don't know the average body temperature for all people. Interestingly enough, 98.6 isn't really, from what I've heard, like, what is the average temperature of humans?
Here's an answer from medlineplus.gov.
More recent research, from what I understand, says body temperatures are a lot cooler. Maybe it's that you get cooler when you're older. That's what I heard. But yeah, 98.6 I think is an outdated number, oftentimes quoted. So a lot of times people have lower body temperatures than that. It's not bad for 98.6, but you know, It's within normal range. So, but they're saying that's the average. Brian's qualms with my Pearson. How's this doing? 89%. Now we're below 90%. We're still approaching 90%. More simulations are needed. Okay, let's go back over here to the question. And we've marked our notation. Now, when we do this, how do we do our conditions? This is practicing for the test. Don't read what my Pearson says. We go condition 1, condition 2, and then we pause, and then we remember we have to think, what kind of data are we working with? The data was, well, condition 1 is random, so we'll make sure it's randomly selected people. Condition 2 is less than 10% of the total population is selected, so this is adults, so 52 adults is less than 10% of all adults. Randomly selected, random is good. Sometimes they break apart random into random independent, so if it's independent, it is random. And as Jesse points out here, body temperature is quantitative, like how much was your body temperature? It's a weird way to ask how much is your body temperature, but the way to know something is quantitative is if you have 2 points of data, and great job, Kat, Meredith, and Jesse. If you have 2 points of data and it's quantitative, you can always take the what between 2 points of quantitative data and it makes sense. Like I have 98.6, you have 99, so now we could do what between those numbers? And then that would make a difference, would make sense. So you could be like, oh, I'm 0.4 higher. So it would make sense, and that means it's quantitative. And so the third condition now is the nearly normal condition, which in great job, Sloan right there, which is going to be checked one of 4 ways. The 4 ways to check the nearly normal condition are, 1, we can look at the shape of the data. If the shape of the data looks like a normal curve, it's good. This does not. 2, we can look at the normal quantile plot, known as a normal probability plot, and if it follows the red line, it's normal. This one does not. 3, we can check the goodness of fit test, which has the null hypothesis that the data is normal. Since the p-value here is low for both goodness of fit tests, two different groups of people made their goodness of fit tests, we would reject that the data is normal and have evidence that it's not normal. If when it does look normal, it'll look this way. So here we are. Look at the histogram. Histogram can be deceptive, though, because of bin widths. So histogram is not the best way to often look at stuff right there, but this does look kind of normal. If we give it a good amount of bins, that is a reasonable amount. Most of them do look pretty normal. Some people might say that's bimodal, but it's pretty normal. Better yet, the normal quantile plot doesn't have bins, so we can see that it follows the red line. Looks pretty normal. Red line is what the normal is, and it follows it pretty closely within the kind of decent range. The p-values on the goodness of fit test are now high, which have us fail to reject the null, meaning we do not have evidence it is not normal. But here's one last thing we can do. We did mention in previous chapters the large enough n. Now, we don't know the shape of the parent population because in previous chapters, we knew what this looks like. We don't know the body temperatures of all people. We only know our sample data. So large enough n really only comes into play when we do have a larger sample size. So if you had a larger sample size, you might be able to infer the shape of your data, infer the shape of the parent population. So now you have inferred that the parent population is probably pretty skewed, or either is uniform or skewed, I would guess from that. So we could infer the shape from the sample data. But here's where you run into a problem. You run into the problem if you have a small sample size. If you only had 2 observations, so tell me, think about this. I want someone to answer this in the chat. Okay, so someone tell me. I'm going to make it so you can't see this. I know you can't see yet either. You might be able to guess it. Sloan, what is the shape of the parent data? You only have 2 observations. What is the shape of the parent data? This is to show you that with sample data, you only have 2 observations now. This is your sample data. You collected 2 observations. What is the shape of the data it came from? What is the shape of the data it came from? This is why we can't always use the large enough n. What is the shape of the data it came from? Take a guess. You might get it. Frankly, we really don't have a good, I would say we really don't have a good way of telling. Maybe someone might get it. I want to see what someone guesses. Meredith, 100 points where we can't tell. I think it would be wrong to infer the shape. I think it's wrong to infer the shape. But I think someone might actually guess it. It's good guess, Jesse, right there. It's not skewed. It is actually bimodal. There's 2 modalities to it with the right skew over there. I was trying to do 2 peaks, and then I dragged this along the bottom. If you had a larger sample size, you'd probably start to see the bimodality. Well, we want to take the sample data. This is the distribution of means, but notice how with a larger sample, you can really start to see that there is probably a second mode over here. So with a larger sample, you would get a better instance of the shape. So all that just to talk about the distribution. We have 52 observations. Does this look heavily skewed? Does your sample data of 52 observations look heavily skewed, yes or no? Does it look heavily skewed? And so we're actually using large enough N right here because we have 52 observations and we have a good idea of what the shape might look like of the parent population. And I would say this is not heavily skewed. It's even the bins are showing me kind of a normalish shape. It's not heavily, like there's a little buildup over here, a little high observation over here of one observation over here, but there's a lot of centrality to the data in the middle and just a little bit of weirdness here. If you draw a normal curve over this, it doesn't look too bad, which is the idea of fitting a normal curve when we talk about the goodness of fit test. Like the normal curve doesn't look too bad. And remember, bins are always deceptive, so I'd say it's nearly normal. 95% confidence interval, this is going to come down to doing the notation right here. So here's where people are going to get stuck. What value are we missing currently? And it was 90%, was it? What value are we currently missing to solve this interval? We are currently missing what? And where do we need to go? This is where people get stuck on these questions. This is the number one spot people get stuck on, the T. So we're going to go over here to the apps. On the app screen, make sure you've clicked student T. Yep. And this what's really great about this, T tables don't always give you the exact numbers. So I always love going to the apps right here because all we have to know is the degrees of freedom. And remember, degrees of freedom are N minus how much? For the one sample T, the degrees of freedom are N minus 1. So we could have also, in our notation over here, marked great job. And technically lowercase, technically lowercase. Sometimes people, I've seen interchanging between uppercase and lowercase. I'm very particular about that, but rarely, I don't think it ever appear on the test. And we need 90%, and we go between. And there it is right there. And great work, Jesse. Great job following along. So here is the T we need. I would probably carry it to a third digit. 1.675. I know, right? I have that happen all the time. More points. We need some new levels. Standard deviation 0.652. And check out earlier in the stream where we talked a lot of the theory about the T. We've covered it a few times, so I'm not covering it again right now for the moment. And we'll be talking about it at the start of class today. So there is the interval, and I always calculate first the margin of error, which is going to be 0. We need to take square root 52 square root, 0.6752, boom. 1.675, we're good, and 0.568, 1568, and 98 plus or minus 689 plus or minus. So now we need to find the lower and the upper of the interval. There's that, 98.846, and then we subtract. 98.532. There we go. There's the interval right there. There's all the work. And now we put in the numbers. So I'm going to bring the page over to the other screen so I can see it as I type it in. Okay. 98. Two decimals. Boop. Boop. Explain the meaning of the interval. Once again, we do not look at their interpretations. We interpret our intervals ourselves. This might be one of the last questions we're doing here today, so don't read their interpretations. I like to say the I am. So don't read their interpretations. This is your time to practice for the test. This is our time. So we need to practice and know how to interpret this without their help. Once again, we can go to one of our sheets where we've written out some confidence interval interpretations where we wrote the I am. blank percent confident that the true blank is contained in the interval blank to blank. So what were we trying to estimate? We had 90% confidence, and then we'll just say our interval is something like 98 to 99. Put in the real numbers, but we'll pretend those are the numbers. So what were we trying to estimate? Then we're going to look at their interpretations and see which one makes the most sense to us after we write our own. I am blank percent confident. So when you get to the test, you'll be like, I am blank percent confident that the true blank is contained in the rule blank to blank. And you know how to do it. You know how to put in what you need, and you're good to go. It's about getting ready for the test. So I am, was it 90% confident that the true average body temperature of people, adults, is contained in the interval and whatever interval we gave. So there is 90% confidence based on the interval, based on the data. The interval contains the... Oh, you see, they're putting adults right here. I 90% confidence that the true adult, great job. Meredith right there, that's worth some 500 points. I think they're... And so they're saying adults right here. So we got to watch out because these are the only ones that talk about adults. So I'm a little worried about this interpretation because it doesn't say adults, and that is some context we probably need because look, it says the adult population is what we're trying to understand. Estimate the average for the adult population. That be very careful. Don't click answer all the questions before I do. We'll always fall in the interval. This is just horribly wrong. Based on the data, 95% confidence that the body temperature for an adult and what's the problem with this? It's not about what, it's about on average, right? What's the problem with this? So I think they're going here, and I don't like the false word, but this is obviously wrong right here. An adult, that's a singular. No, we're talking about the average among the adult population is what we're trying to understand. So this one's wrong because it's a singular adult. Boom, Meredith, you're seeing it right there too. Yep. So because we're talking about the true mean would be the average for all adults. So yeah, the body temperature for all adults, which I prefer they just say true mean. Body temperature of all adults is the mean. Explain what 95% confidence interval means. Well, we have a simulation showing us what it means. 90 or 95% confidence means in the long run, like law of large numbers, look over there at the data. It now shows that 90% of 90% confidence intervals in the long run. There might be decimals beyond this, but the simulation has converged towards 90% and has rounded to it. So 95% of all such random samples will produce intervals that contain the true mean temperature. That does sound correct. 95% of all sample sizes of 52 have a mean. No. 90%, no. It is 95% of... Ooh, wait a minute. Are we making 95%? Jesse, I have an error in this question. This is the wrong z-score. I used 90%. Dun, dun, dun. 2 point... Oh, it's basically 2 for all intents and purposes. That's why software is much better to solve with. Okay, 52 square root. There's that. 1.188. Yeah, it's so easy. How many eighths was that? 2 eighths. And that rounds to 9 then. No, it's just 8 8. Okay. 9 8 6 8 9 plus 0.188. There's that. 9 8 7 8. There's that. And then right here minus 9850. 5088. 5088. Just a little wider. That should be correct now. A temperature of 98.6 is assumed to be normal since it contains it is believable. We should be good. What? Did I mess up my interval again? Let's just see right here. Is it the interval? Last question of the day. We can't make errors. It is not the interval. Whoa. Really? 98.88. 98.50. Seriously not doing that to us, right? That is just wrong. That is just wrong. If you got that, that is just wrong. That is That is just wrong. I was like, that was the only other thing I could think about. That's just wrong. Please email me if you got that wrong. If you're watching this video in the future and you got that, that is my Pearson. Come on. We wrote our interpretation. What's wrong with the lower answer? I guess because they didn't put mean. Like literally this, like that's what I was talking about as we were saying it. I'm like, well, the body temperature for all adults, it's not like, if you think the body temperature of all adults is the mean body temperature, well, it doesn't say mean. It's just neither answer. Like this one's missing context and this one's not using mean. But remember when we wrote our interpretation, I can literally read it to you. I'm going to pin the message right here. And Jesse even put 95% confident. Jesse put, one is 95% confident that the true average body temperature, literally right there. And then I would put the adults, so we put together what Meredith said and what Jesse said. So yeah, that's a little, yeah, what are we trying to estimate? The true mean. And it literally says up here, the true mean among the adult population. It's not all body, contains the mean body temperature. What? For who? What's the context? That's, someone wrote a question to get people to miss things. So I'd love to show that to like multiple statisticians to see which one they say. See, it's the problem is it's not the perfect answer because it doesn't have context. Sometimes I wonder who writes my Pearson questions. And I'm like, maybe it's like someone who hasn't done as much stats as we have. So maybe not as much as I have. I'd hope they've done as much as I have. I guess I've been doing this a little while. And I do want to point out, the last thing I'll say right here is, a lot of times when we're doing statistics, if you're creating a confidence interval, this is how we create a confidence interval in the real world. Like, let's say I want to figure out what the average weight of a male is or the average weight of a student is. Well, I've got data right here. And so we bring up the data from Survey 10, and then we run here t-dot test on it, which is also going to do the t-interval. We bring up the Survey 10 data, and then we bring up the weight, and we go right there, and I am 95% confident the average weight of a student is contained in the interval 152 to 158. We could look at the distribution of weights also, just to make sure it's normal. I think it's got some skew to it, but this is a very large sample size. The figure's too large for the margins. So we bring this up right here. We just take a look. It is right skewed. It's going to have a little bit of oddity on it with the normality plot. So you notice there is some pull away from the normal distribution. It's going to fail a goodness of fit test. So we run the goodness of fit test. So we run the Shapiro-Wilk. That's the thing you saw elsewise. It does fail with low p-value. But due to the large enough n, the sample size of 699 right here is going to be, and we could double check by going here to length of the vector. So I could just keep copy pasting the vector with the function around it. And there are 699 observations. So we have good reason to believe that the large enough n is passed, that the interval is valid in its assumption of normality for the distribution of the mean. If we wanted to do just males right here, we could load up our library dplyr. Yay! Oh no, there's other people here. Good to see you here, Didi. We're ending office hours here in 7 minutes, and I'm kind of showing just a little bit of like the application of how we do these things because we just got tricked by my Pearson problem. 100 points for Didi being here. So what we have right here is the Survey 10 data. We can actually use what's called a pipe in R to filter, and we can go here gender equals male, and so that's only the males right here. And then we can bring it through and do t-dot test on this. Or we could just store this as just males, and that creates the data set. And then we do a t-dot test on males. And on the males data set, we can look at the weights of males. And I am 95% confident the weight of a male is contained in the interval blank to blank. So we can interpret that way. We can also compare the weights between genders pretty quickly with the associate function. And we can go right here and say associate the weight explained by gender. That's a formula format, y tilde x. So what I've put right there is one argument. Oh, awesome. Got all the happiness in the chat. Love it. And then data equals and Survey 10. I'm going to show you one last cool thing too. So this is running the analysis for the comparison between the means and medians. So you can see the differences between the average male, the average female right there. The medians, there's a pretty large difference of 45-pound weight difference between median male, median female. Between average, there's like a 43-pound difference. Just subtract these two numbers to find the differences. But what's really, really cool is if you want to look at correlations in a data set, a lot of times people use core.matrix. Now, correlation matrices can get pretty out of hand quickly. This is what we learned in chapter 6 is a correlation matrix. But this is a larger data set with a lot of quantitative variables. So when you get a correlation matrix, it's going to take up a whole ton of your screen. It has to actually wrap around the screen and give you all these values. But we actually have a much better function for looking at correlations. And the name of the function is all correlations. So the all correlations function, as it says, gives us all the correlations. So we'll get the output nice and neat right here so we can see it. So we literally have every correlation in the data set. And you might say, well, how is this better than a big matrix? Like, why would you want all the correlations right here just shown to us? What we can add to the function is we can add an extra argument and say interest equals weight. And now we only see things correlated with weight. So now we only have the variable we're interested in and all the correlations in that data set for the variable weight. But wait, there's more. Weight spelled differently. We can go right here and go to sorted and equals magnitude. And guess what it does? It puts the strongest in terms of absolute value correlation first. So now we know the things most associated, and it doesn't matter, as the Rock always says.
It doesn't matter.
If it's positive or negative, because we're just looking at the absolute value of the correlation, which is the strength of the correlation, which is what we learned in 201, that closer to negative or positive 1 is the strength. And last question of the day worth 500 points. Things that are stronger for equal sample sizes are more what? Things that are stronger, so a stronger correlation, closer to 1 or negative 1, will actually be for equal sample sizes. So for equal sample sizes, the same data set, a stronger correlation will be more what? Lower p-values, more statistically significant. More statistically significant. 500 points right there, DD, earning it for the class. Does that make sense right there? Like, it's more significant to have a stronger correlation, all sample sizes being the same. I do want to point out one trick, though. Is a correlation of 1 statistically significant? So is a correlation of 1 statistically significant? Be careful. Is a correlation of 1 statistically significant? Think, why am I asking this? Is a correlation of 1 statistically significant? Is a correlation of 1 statistically significant? X and Y have a correlation of 1. Is a correlation of 1 statistically significant? Think over this for a moment. Any 2 points. Oh, Y limb? Infinite Y limbs? Doesn't it? It is perfectly linear, exactly. Let me put in another data point right here. Did not like because there's only 2 data points. Any 2 points. There it is right there. I'm going to try to bring it back to 2 points again. Interesting, Petry's function doesn't work on that. Plot x comma y up to O data equals. Any 2 points. Ooh, same root cause. I like that. Any 2 points will always be connected by a line. Any 2 points will always be connected by a line. So when you look at the statistical significance of this model, here's the thing. Core test for correlation on y tilde x or y comma x. Data equals, or we got to do it with data. Data $y comma data $x. Oh, called it df this time. It can't run it. And for small data sets, high values of correlation might not be statistically significant. If you look at the slope of the line, it doesn't even give you the standard errors. You can't even estimate standard errors. Now, if we bring this up to 3 points, I think we will get those values. So this is now where we have 3 values. And so if you have a small data set, you can't even get those values. And you see it's still saying there's problems for some of this right here because of the small data set and the perfect fit. But in the previous, with only 2 values, it wouldn't even give us a p-value, which the p-value of the slope right there is going to be the significance of the model. So we didn't even get a p-value. With 3 points, we are able to get a p-value. Yep. So you have to be careful because if someone says they have a really high correlation, they could have just had a very what? So if someone had a very, very high correlation, they could have simply had a what? I have to go to... If somebody had a very high correlation, it could be because they had a what? Very little data. So probably this right here, I wish it showed the p-value on this. So look over here. There's the correlation right there. It could be, yep. And so this might not be statistically significant. So small data sets have low statistical power. This actually branches into the idea of statistical power. So when you have a small data set, so Jesse, this is chapter 16, Didi is like chapter 16, I think. We're going to be doing this like in a week or so. Small data sets have low statistical power. Low statistical power is basically the inability to find results. So you wouldn't have evidence of a correlation here. Likely, I know I don't have a p-value on the screen, but we could have the same correlation of 0.8 with more data. And then at this point, you see how I got to make it even tighter. A correlation of 0.8 with more data. There we go. Let's make it 0.8 exactly. And you can just kind of think about it conceptually. At this point, you'd probably have a lot more evidence that there is a correlation right here. You'd be like, okay, the correlation of 0.8. Hey, can you calculate p-value and correlation for a Nicholas? Yeah, well, they don't do the spurious correlation. You probably know that website. We could. Is it publicly available? Spurious correlations, Tyler. No, we're just ending off right here. Okay, his website's back up. So, oh, that's great on the screen. Here we go. He does this one. Nicolas Cage and drowning in a pool right there. So he looks at the correlation of this. The correlation is 0.666. That's woo. And you can look at the data. He gives you the ability to search data and look at spurious correlations. So I thought maybe he removed that. But if you run enough data, you will eventually find something that's pretty much due to random chance. And I was like asking people, with a 0.05 alpha, what % of the time do we find results by random chance? Oh, this isn't working. Yeah. Oh, hey. There it is. He removed it. We used to have that. Yep. He finally took that link down. With the 0.05 alpha, we find results that are due to random chance 5% of the time. That's your type 1 error rate. And so you will find things that you think are correlated and have, something going on right here with a strong correlation. Like these two graphics follow each other, but turns out it's just spurious. Or it could be due to a lurking variable. So pretty good right there. Letters in winning word of Scripps National B, people killed by venomous spiders. So, man, that's really venomous spiders are not that scary. No, they still are scary to me. So with that, we'll be back. We'll have class in a little bit. Good to see you, Didi. Good to see you here, Jesse. Good to see you here, Meredith. Bye for now, everyone. Bye.